Okay, guys, this is 8.5. It's alternating series test. This is the easiest test in the chapter. You're going to love it. To review where we stand right now, you've got all series whose terms approach zero are allowed in this bubble. The ones that do not diverge automatically. If the terms are not going to zero, then infinity of them have no chance to converge. Now, of the ones that do go to zero, we are letting them in this bubble, and now we are sorting them out. We are saying, okay, if you are a certain kind of p-series, you're on the left. If you're a certain kind of p-series, you're on the right. We can use the integral test to sort them out left to right. We can use comparison of series to sort them out left to right. We've got a lot of ways to sort them out left to right. This is the easiest one yet. Of all terms, of all series whose terms approach zero, we're going to see a bunch of them today that look like this. The sum from 1 to infinity of -1 to the n over natural log of n plus 1. Okay, so first of all, you're going to see in this section a lot of these and a lot of these. So let's just get that out of the way. The -1 to the n and the -1 to the n plus 1. All that does is it provides a negative sign for every other term, thus making it alternate. Okay, so that has nothing to do with it. It adds a lot more detail to the formula, but it doesn't change the value of the numbers whatsoever. If it's -1 to the n, and we're starting with n equals 1, that means our first term is going to be -1 to the first, and our first term will be negative. The only reason we have two versions here is if we're starting with term 1 and the first term is positive, then this n plus 1 will make it -1 squared, which won't change anything at all, and the first term will be positive, and then the second term will be negative. But those two things, when you see those, just automatically know this is going to make these signs alternate, but that's all it changes. Okay, so let's talk more about this specific series. First of all, do its terms approach zero? Its terms are basically 1 over the natural log of n plus 1. All right, forgetting the alternating for just a second. Now, natural log is weakest on the hierarchy of domination, yet it still does go to infinity. So 1 over it still does go to 0. These terms, if I expand it out a little bit, my first term is negative because of that -1 to the n on top, and I have on the bottom natural log of 2. My next term is positive, 1 over natural log of 3 minus 1 over natural log of 4 plus 1 over natural log of 5, and so on. Now, under normal circumstances, if this were just all positive, we know they approach 0, and then we have to use some sort of test to sort it out. Does it converge or diverge? Here's the great thing about the alternating series test. If a series alternates and the terms approach 0, then the series converges. So what that means is if you look at a series and think, oh, this alternates. I see this -1 to the n or this -1 to the n minus 1. If you see that, the only thing you have to do is say, do the terms then go to 0. If they do, then it converges. It's like the alternating gives it this extra power of convergence. And if you think of it, it makes sense. We are trying to determine if we add up infinity terms, if they can still add up to some finite amount. Well, if you take every other term and make it negative, therefore taking away from your total, it would be a lot easier for it to add up to a finite amount, because we're not adding on and adding on and adding on. We're taking away every other term. So, according to our Venn diagram, the first thing you always do is look and see, does it have terms that approach 0? If not, you're done. It doesn't matter if it's alternating or not. That's the very first check, the nth term test. Now, if it does have terms that go to 0, all you have to say is it alternates, it converges. So, over here on this convergence side, all alternating series converge, assuming that they pass the nth term test. Okay, you're going to get a lot of answers of alternating series convergence, because if it doesn't converge, actually you will only get the answer it converges by the alternating series test. You're never going to get diverges, because if the terms don't go to 0, it's not allowed in the bubble anyway. So it failed the first level of testing. So any alternating series that gets in the bubble has automatic VIP passage over to the left side. Okay, so just another couple quick examples. How about the sum from 1 to infinity of -1 to the n plus 1, so it alternates, times n squared over n squared plus 5. All right, so first of all, this just makes it alternate. That has no bearing on the size, on the magnitude of the terms. So all you have to do now is look at n squared over n squared plus 5. And what does that tell you? Well, those are both quadratic. They both have a coefficient of 1. So these terms don't approach 0. They approach 1. Whether they're alternating or not, it doesn't matter. They're not going to 0. So this diverges by the nth term test. Okay? It does not converge or diverge by the alternating series test, because the first screening process you have is it's got to approach 0. If it had approached 0, then instantly it alternates, it approaches 0, the whole thing converges. One more example. How about -1 to the n plus 1? And on top we're going to have a natural log of n plus 1. And on the bottom we are going to have an n plus 1. Okay, so the alternating part, we know it alternates, but don't take that into account as far as whether the terms do or do not go to 0. They're going to be either alternating. If terms that go to 0 might do it like this, or they might do it like this. Either way, they're going to 0, whether they're alternating or not. So the alternatingness of the series doesn't have anything to do with the limit being 0 or not being 0. So it alternates. So if I can decide that these terms approach 0, then I can say that the whole thing converges. Not just the series, the sequence of terms converges, but the whole series converges. That's the power of the alternating series test. So what do I have? I have natural log on top, and I have linear on the bottom. Now natural log does go to infinity, and linear does go to infinity. However, natural log is the weakest of all infinities. Even just a straight line will end up dominating natural log in the long run, because natural log infinity is slow, and linear infinity is mediocre. So in the long run, that red will dominate, and the bottom will get huge, while the top gets huge slower, and therefore this does in fact go to 0. So terms go to 0, it alternates, so we have convergence. That's it. That's probably not the most technically sound way to answer this question, but For the most part, you're going to be answering this in a multiple choice on your AP test. So the thought process you can have in your mind is the terms go to zero, it alternates, it converges. You're not going to, in an AP situation, have to prove this or explain it in much more depth. So for that reason, I'm not going to ask you to explain it in much more depth. You need three pieces of this answer. The terms go to zero, the terms alternate, it converges. All right? So that's the test. A couple more little things in this section. All right, we have convergence. Now that we have alternating series, we have two different levels of convergence. All right? A series that converged anyway, before it alternated. Like, I don't know, a P series that converged. This was 1 over 1 plus 1 over 4 plus 1 over 9, 1 over 16. This converged, even though the terms were all positive, this converged by the P-series test. If it converges and all the terms are positive, that's called absolute convergence. That's like the legit, it's not a poser convergence, it's an absolute convergence. It converges anyway, it doesn't need any extra help. Sometimes, basically, any series that lives over here is conditionally convergent. If it lives over here, its terms go to zero. Because if its terms don't go to zero, then it's not allowed in the bubble to start with. But if its terms do go to zero and it diverges, then we make it alternate, then that makes it converge. So any divergent series whose terms do go to zero is called conditional convergence. A perfect example is a harmonic, which is a P series with P equal to 1. 1 plus a half, plus a third, plus a fourth. It diverges because we know the harmonic series diverges, and it's a P series with P equal to 1. The harmonic series, the terms do go to zero, yet it still adds up to infinity. This is what's called conditional or conditionally convergent, because under the conditions that you make it alternate, then we've changed it from diverging to converging. All right? If the terms go to zero, which they do, and if it alternates, which they do, it converges. But it converges conditionally. The only way it can converge is if you give it the extra help of making it alternate. So that's the difference between absolute and conditional convergence. One more thing. Let's take an alternating series which converges, like the alternating harmonic. I told you many days ago that almost always we don't say, hey, I know what this converges and I know it adds up to 7. We don't know what they add up to unless they are geometric or telescoping. We don't actually know what the sum is. We just say it converges, and I know it by one of these tests. An alternating harmonic, you still can't add it up. You can't say, hey, I know an alternating series, not just the harmonic, but any alternating series. You still can't say, hey, I know this adds up to 14, or I know it adds up to 3.8, or I don't know what it converges to. I know that it converges because the terms go to zero and it alternates, but I do not know what it adds up to. So the point is, I can get close to knowing what it adds up to. Here's your rule in my words. An alternating series my words again. The first n terms of an alternating series are within the n plus 1th term of the true sum. For example, 1 minus a half plus a third minus a fourth, it adds up to some finite amount. What is it? I don't know. But if I add up these first 7 terms, I know that I am within the size of the 8th term of the true value. So let's figure this out. If I add up 1 minus a half plus a third and so on and so forth, let's see what I get. 1 minus a half plus a third, minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh. Okay, got all those minus plus minus plus. So my first 7 terms add up to 0.726109. Let's call it 0.72619. 72619. Now, how close is that to the actual sum of this convergent series? Well, whatever my next term would have been. My next term is negative 1/8. And the plus or minus of that next term doesn't matter. What I know is that however many terms I decide to add up, I'm within the next term of the actual answer. So 1/8 is 0.125, right? So I can take that number minus 0.125 and get 0.60119, and then 0.72619 plus 0.125 plus 1/8 is 0.85119. So 60119 and 85119. 60119, 85119. Right? That's right. So the true sum, we've been saying this series converges forever, for weeks. And we just say it knowing that it adds up to some number, but we have no idea what that number is. Well, now I have an increasingly good idea what that number is. I know it's between 0.60119 and 0.85119 because in alternating series, the first n terms are within the n plus first or n plus 1th term of the true sum. Okay, so I hope that makes sense. We can talk about it more in class, but I think that's good. So if I want to get closer, I just add some more terms. You'll have some problems where you have to get within a certain sum, so that'll just be finding the term that's smaller than that margin of error. All right, so my true sum is somewhere between these two. All right. So that was longer than usual, but this is a quick series to use, and we're getting close. One more section, and then we will be ready to start thinking about test time. We'll get to that in class. I will see you then. Young out.